Hello guys, this is the Unit 4 test from October of 2022 and we will just solve it, I guess. Before we do so, let me show you where I find these papers. Okay, so this is a website called Paper Lords. Okay, so let me go to the landing page. So yeah, this is it. I'm gonna have the link in the description. So if you go here at Edexcel International Recent Papers and you click Physics, then they list the most recent papers pretty much up to May 2025, which we went through, I think, in my videos. So anyway, okay, let's go back. So there are other websites as well that have these past papers, and there are many Discord servers. Just search A-level physics Discord. You will find many open forums that you can join and find information and so on. Let's start. So, section A, question 1. Which row of the table describes the mass and charge of the antiproton? Okay, I remember the mass of the proton by heart, but it's easy to, okay, one of the techniques that you can use in section A is that, okay, if you look at these answers, immediately the last two, I mean, these two are wrong, right? You cannot have negative mass. So you're left with option A and option B. So even by chance, you have 50% chances of getting the question correctly. But you have to remember that the proton has a charge of plus E, and E is 1.6 times 10 to the negative 19 coulombs. Therefore, the antiproton has an opposite charge, right? So B, easy as that. Question 2. Which of the following is a valid conclusion from alpha particle scattering experiments? Okay, atoms contain positive and negative charge distributed evenly. That's not really a conclusion from Rutherford scattering. So let's move on. Option B. The nucleus of an atom contains protons and neutrons. Actually, this is wrong because they didn't know about neutrons at the time. Okay, I mean neutrons were discovered. Okay, because I do this on the fly. Okay, I don't remember my dates correctly, but I think the Rutherford scattering was something that was performed around 1915, something like that. Whereas neutron was not discovered until 1932. Actually, let's take a detour. I'm sorry. So let's see. When was the neutron discovered? Sorry for wasting your time. So by Anderson, I think. No, James Chadwick. Okay, 1932. Okay, I was correct. Good. Anyway, let's go back. Option C. The nucleus of an atom is very small compared to the size of the atom. Okay, that's sounds good. Let's see option D. Atoms contain very little empty space. That's totally wrong. Okay, so C is the correct answer. Question 3. Which of the following describes why electrons are released from the metal filament during thermionic emission? Okay, option A, the metal filament is heated by an electric current. Okay, that sounds good. B, the metal filament is contained within a vacuum. Doesn't play any role. Option C, the metal filament is bombarded by high energy electrons. No. And option D, the metal filament is maintained at a high potential. That's not necessary. So A is the correct answer. Let's go to option 4. Question 4, I don't know why I keep saying option. So the diagram shows the shape of the electric field pattern between two charged particles X and Y. X has a charge of minus Q. Which of the following could be the charge of Y? So, okay, we have to think about it. First of all, it has to be negative, okay? How do we know that? Because for positive and negative, for negative and positive, so if Y was positive, the lines would look like this. They would close, okay? but now the lines repel, okay, which means that we have a negative charge for y, okay? So immediately we eliminate these two options. Now you see that the lines around here are denser compared to here, so therefore there must be more charge on y. So B is the only possible answer, okay? Simple as that. Again, you see how you can just eliminate logically. I mean, immediately we eliminated 2 out of 4 options, and then immediately we see that, okay, the lines here are denser, therefore we have more charge here, okay? So immediately, just by logic, you can find the answer, okay? Question 5. The graph shows how the charge Q stored on the plates of a capacitor varies with the potential difference V across the plates. Which of the following expressions give the energy in joules stored by the capacitor when V is 12 volts? Okay, it's pretty much the area under the curve, remember that? So what's the area under the curve? 1/2 base, which is V, times height, which is Q. So Q times V. Okay, so we have to read the options, and the only option is, okay, this is nanocoulombs. So 550 times 10 to the negative 9 times 12, which is the voltage. So yeah, option D is the right answer, okay? So I hope this makes sense. Also, if you go to the back of your paper there, they probably have this, they list these formulas. Let me check. Unit 4. Yeah, energy stored in a capacitor. There it is, okay? So let's go back. Where were we? Here, okay. Okay, 6. The SI unit of magnetic flux density is the Tesla. Which of the following gives the base units of the Tesla? Okay, the way I do things, the way I solve problems like this is to use a formula that naturally introduces a unit. So let's try the force on a charged particle moving with velocity v inside a magnetic field is given by QVB, okay? So remember those square brackets I like to use whenever I work with the dimensions or the units of a quantity. So we can use them here and solve for B, okay? So B is F. What are the units for F? Newtons. Over, what are the units for Q? Coulombs. What are the units for V? Meters per second, right? But Newton is not a fundamental. I mean, it's not expressed in base units. Now, in Newton in base units, you have to remember that F is MA, right? So, hope this is not confusing. So, okay, let's use the square brackets, which denote the units of a quantity. So, newtons is kilograms times meters over second squared, right? So, let's go replace that. Okay, I need some space over there. So, we have kilograms meters over second squared, and then we have coulombs, meters, and seconds. So these seconds go away, the meters go away. So kilograms times seconds to the -1 times coulomb to the -1. But then coulomb is also not a fundamental quantity, I'm sorry. So we have to remember that coulombs is amperes per second. So okay, actually let's take an extra step. Sorry, I just thought about it. So kilograms over seconds, and then coulombs are amperes over seconds, right? Wait, I is Q over T, so Q is I times T, so coulombs is amperes times seconds. So I made a mistake again, don't know what's wrong with me today. So amperes seconds, so the answer should be kilograms amperes to the -1 seconds to the -2. Is there such an answer? Yes, that's option C. Okay, hope this makes sense. Moving on, option, I keep saying option, I don't know why. Question 7. The table shows the relative charges of up and down quarks. Okay. Which of the following could be a quark composition for a baryon with charge of plus 2e? Okay. Okay, these two are obviously wrong because those are mesons. Okay, so we are left with option A and D. A will give you a negative charge, so it's D. Okay, let's verify. So 3 times an up quark that has a 2/3 E charge gives you immediately plus 2E. So D is the right answer. All right. Question 8. I'm sorry. A LINAC is a particle accelerator. It consists of drift tubes of increasing length with potential difference applied between them. Which of the following is the reason why the drift tubes are of increasing length? Okay, without reading the answers, it's because the frequency is constant, I guess. So let's see. Option A, so that the potential difference can have a constant frequency. Okay, that's that. Correct. That's A. Let's read the other one. So the particle gains the same amount of energy in each tube. No. So that the potential difference between the tubes increases for each successive tube. That's not correct. And D, so that the time spent in each successive tube increases. No, because it has to spend the same amount of time. That's why, because the frequency is constant, right? So the particle spends the same amount of energy, time, sorry, inside of each tube, right? But because it travels faster, the tubes need to grow in size as the particle moves in the LINAC. Okay, let's go to question 9. An object of mass m has momentum p and kinetic energy E. Which of the following is the mass of an object with momentum 2p and kinetic energy 4e? Okay, so the energy of the first particle is just p squared over 2m. So m is p squared over 2e. Okay, let me think. Okay, for the particle that has a kinetic energy of 4e, okay, 4e, okay, let me think. I confused myself. Okay, an object of mass m has momentum p and kinetic energy e. Okay, so that's the first particle. Which of the following is the mass of an object with momentum 2p and kinetic energy 4e? Okay, so 4e would be, okay, actually, let's solve for the mass immediately. So m prime would be 4p squared, right? Okay, m prime will be p prime over 2e prime. Okay, and we are told that p prime is 2p, so we have 4p squared, and in the denominator we have a kinetic energy of 4e, so we're going to have 2 times 4e, so the 4 with the 4 cancels, so we are left with what we started with, so m prime should be m, so the answer is actually B. I hope this makes sense. It's a little bit confusing the way it's stated, but I hope my solution makes sense. Excuse me. So, two coils L and M are placed next to each other as shown. An alternative M is induced across coil M. Which of the following could produce this? Okay. An alternating current in coil L. Okay, let's think. So if there's an alternating current, a magnetic field, okay, let's take L. So let's say that there is a current I, which according to, if we use our left hand, it's going to induce a magnetic field B in this direction, okay? You have to curl your fingers around the coil, pretty much around the direction of the current, and your thumb is going to point in the direction of the magnetic field. But because the current is alternating, B alternates between in and out of M. So the magnetic flux density in coil M changes, And that, yes, can actually induce an EMF. So A sounds correct. Let's see option B, a constant current in coil L. A constant current will create a constant B either in this direction or in this direction, okay, perpendicular to the coil M. But a constant current will generate a constant magnetic field, so no magnetic flux density changes, so that's wrong. Option C, and decreasing current in coil L, but and decreasing current will go to zero eventually, so there will be no change, except briefly, okay? There will be no change in magnetic flux density, so that's wrong. And the same goes for D, so the only correct answer is A. All right. This was not hard, but not easy either, okay? I mean, it kind of challenged me a little bit, so let's go to section B. Question 11. Okay, this is a 6-mark question, so it should take you 6 minutes. Remember when I keep saying that all the time in my solutions of past papers, that the marking should be an indicator of about how much time it should take. Okay, so 1 minute per mark, something like that. But okay, don't freak out. Don't become a policeman of yourself. So something like that. Question 11. Pions belong to a group of particles known as mesons. State the quark structure of mesons. So mesons consist of a quark and an antiquark. Simple as that. Muons belong to a family of particles known as leptons. State one property of leptons. Okay, so they are fundamental. So leptons are fundamental particles with a lepton number L equals to plus or minus 1. Okay, that's one property. Okay. Question C. Charged pions usually decay into a muon and another particle X, as shown by the decay equation. A student suggests that X is an antineutrino due to particle conservation laws. Deduce whether the student is correct. Okay, so when you have a pion, negative pion, decaying into a muon plus another particle, first of all, we have a conservation of baryon number because we go from a baryon number of 0 to 0 because no baryons are involved, okay? So let's investigate the conservation of lepton number. So the pions have a lepton number of 0 and the muon has a lepton number of plus 1. So if X is an antineutrino, it will have a lepton number of minus 1. So we will have a lepton number of 0 on the left hand side. So that makes sense. The charge is minus 1 for the negative pion and minus 1 for the muon. So, and if X is an antineutrino, it will have no charge. Therefore, the student is actually correct. So the student is correct because if X is an antineutrino, it will have L equals to minus 1 and C charge equal to 0, and the reaction will be allowed. Okay, so that's a good start for section B. Let's move on. I see a capacitor. I don't really like capacitors. I don't think I ever mentioned this before, but okay, let's move on. Question 12. A defibrillator is a device that can restart a person's heart. Okay, that's scary. The defibrillator applies an electric current to a person's heart for a short time. The defibrillator uses a capacitor circuit. A person's body has an electrical resistance of R. A simplified circuit diagram is shown. Okay, so I guess this is the person. So resistance. Okay, the capacitor, we have switches. Okay. Question A. When the capacitor is completely discharged, the two-way switch is moved to position S1 at time 0. Complete the graph to show how the current varies with time until the capacitor is fully charged. Okay. So I wonder. Okay. Now I'm a little bit confused again. Okay, for this, for charging a capacitor, the relationship, actually, I'm gonna need a clean page. So current drops via the exponential formula e to the minus t over RC. Okay, so my hesitation has to do with the fact that do we just draw something like this, or do we actually specify numbers? I guess we have to specify some numbers, like what's the initial current, what the decay constant is, and stuff like that. So okay, I mean, just by drawing this, an exponential decay is correct, but we need to actually specify the numbers. Okay, so okay, let's go to the clean page. The time constant T is equal to RC, and R is 65,000 ohms and C is 34 microfarads. So 65,000 times 34 times 10 to the negative 6 gives us 2.21 seconds for the time constant. I naught, this guy over there, is can simply be found by dividing the voltage with the resistance, right? So V over R, 5,000 volts, it is stated there, over 65,000 ohms gives us 0.076 amps, or 76.92 milliamps. Okay. Let me think. Okay. So at t equals to a one-time constant, I is going to be 0.37 I naught, which is 28.46 milliamps. Okay, that's another point we can use in the graph. Are we good to go? At time equal to 5 time constants, I will be I naught e to the minus 5 tau over tau, which is about I naught over 1000. Okay, so that's about 0. Okay, so we have many points. So at time equal to 0, the initial current is, let's put it 76.92. Actually, they ask to use amperes, so it's 0.076, okay, at time 0. And at time to 2.21 seconds, we get something like that, 0.028 amps, okay. And at time about 10 seconds, we get 0, okay. So we have this data point, we have this data point, and this data point. So the curve will look like this, okay. I hope this makes sense. Okay, moving on to B. The capacitor in the defibrillator, discharges when the switch is moved to position S2. The defibrillator is required to deliver a discharge current of at least 30 amps for a time of 2 milliseconds. A typical person's body has an electrical resistance of 150 ohms. Okay. Deduce whether the design of the defibrillator meets the requirement. Okay, so let's find the time constant. It's 150 ohms times the capacitance. So the time constant is 5.1 times 10 to the negative 3 seconds. Okay. The current is going to be voltage over R. So 5,000 over 150. So 33.3 amps. So that sounds good because they ask for 30 amps. But do we have a problem? Let me think. So it needs to be delivered for 2 milliseconds. Okay, so let's divide 2 milliseconds with the time constant. So 2 times 10 to the negative 3 over 5.1 times 10 to the negative 3 will give us let me think. Do you actually need a calculator? So 2 over 5.1, so 0.39. So what I'm trying to say is that since the time constant is 5 milliseconds, okay, this means that in 5 milliseconds, the current will drop to, in 5 milliseconds, current will be 0.37 times 33.3 amps, okay. So 33.3 times 0.37, the current will drop to 12.32 amps, okay. But what will be the current in 2 milliseconds? So let's use this formula. I is I naught times e to the minus 2 over 5.1, okay. So that will give us, I actually did this wrong in my notes, so I have to do it again now live with you. So let me think, e to the minus 2 over 5.1, 0.67. So this is 0.675. So let's say 0.68 times 33.3. So in two milliseconds, the current will drop to 22.5 amps. So actually that's not suitable because we need it to be at least 30 amps for 2 milliseconds. So this will not work. Okay, because in 2 milliseconds it's going to drop below the threshold. So no. Okay, question 13. The proton antiproton collider SPP-BAR-S was a large particle accelerator. An experiment using the SPPS proved the existence of a particle called a Z boson. The mass of the Z boson is 91 GeV over c squared. Show that the mass of the boson is nearly 100 times greater than the mass of a proton. Okay, this is a kind of an easy thing to ask for 4 points. Okay, so mass of the Z is 91 GeV over c squared. Okay, let's convert this to kilograms. So that's 91 times 10 to the 9 electron volt, 10 to the 9 electron volts, and 1 electron volt is 1.6 times 10 to the negative 19, right? And then we have to divide with c squared, so 3 times 10 to the 8 squared. So in kilograms, the mass is 1.62 times 10 to the negative 25 kilograms, okay? So let's just do the division, mass of the Z over mass of the proton. we have 1.62 times 10 to the negative 25 over kilograms, okay, over 1.67 times 10 to the negative 27 kilograms. Okay, we delete that. Gives 96.87. That's a pure number, very close to 100. So that's actually right. Okay. B. Protons and antiprotons were accelerated in the SPP bars to very high energies before they collided. Explain why the protons and antiprotons needed high energies to produce the Z boson. Okay, so this is a writing problem. So since, let's answer this, since the Z boson is 100 times heavier than the proton, and since mass and energy is conserved during a collision, oops, I'm sorry, comma, we need protons to have high energies in order for all the energy to be converted to mass and produce the Z boson. Okay, so the protons by themselves, like a proton and antiproton, have a mass of 2, say, okay, but we need to produce a mass of 100. So how is this possible? By accelerating the protons to really high energies, therefore we create mass, okay, according to special relativity. Okay, option C. Again, I don't know why I keep saying option, I'm sorry. Question C. Z bosons produced by high energy collisions can have a range of lifetimes. The Z bosons with the longest lifetimes are those that were moving very fast. Explain this observation. So this is time dilation, okay? So it's a straightforward answer. At relativistic speeds, and those are defined as velocities that are larger than or equal to about 0.1 times the speed of light, okay? So at relativistic speeds, time moves slower, okay? Thus, due to time dilation, particles, in this case Z, live long, okay? All right. Question 14. Okay, this asterisk means long writing, okay? So a student uses a strong cylindrical magnet, this guy, to investigate Lenz's law. The student records the time taken for the magnet to fall through two hollow tubes of copper, tube A and tube B. The two tubes have the same length and cross-sectional area. Tube B has a vertical slit cut into it as shown. Okay, so that's the vertical slit over there. Okay, what's the question? Discuss the differences in the time taken for the magnet to fall through each tube. All right, so tube A and tube B is open. Okay, so let's see. For tube A, okay, As the magnet falls through the tube, we have a change in the magnetic flux that goes through the tube. An induced EMF, oops, this should be an M, okay, will be generated according to E is equal to minus delta phi over delta T, okay? In a way, so this EMF will be generated in a way that counteracts the reason that created it, okay? And the reason that created it is the change in phi, the magnetic flux density, okay? Since we have a closed circuit, so it's a closed loop for loop A, a current rotating counterclockwise will be induced which will generate and be, I mean the current, the induced current will be induced, which will generate a B, a magnetic flux density, in the opposite direction. Okay, the magnet will fall through, so thus the magnet will fall slowly, okay, because there will be an opposite magnetic field pushing it up pretty much, okay. For tube B now, the vertical slit prevents a current from being generated, okay. Since we don't have a closed loop. So the magnet will fall through fast. I hope this makes sense. So in this case, we will have a current. Is that counterclockwise? Let me think. Yes. So this current, okay, there will be something like that, like a current through this tube, which will generate a magnetic field density B upwards, pushing the magnet upwards, which means that it's gonna fall slowly. Here the current cannot flow because of this slit, right? So there is no induced current, therefore the magnet will just fall under the influence of gravity, okay? Okay, question 15. Alpha particles were chosen by Rutherford for large angle scattering experiments. Explain why alpha particles are more suitable for these experiments compared to beta particles or gamma rays. Okay, we can say that alpha particles have a charge of plus 2e, so electrostatic interactions are stronger, okay, than for beta particles, which have a charge of minus e, or gamma, that have no charge at all, okay. Also, alpha particles are heavy. They have about the mass of 4 times the mass of the proton. Thus, they are not easily deflected by electrons, and they can transfer more momentum. Okay, B. The scale diagram shows two equipotential lines in the electric field around a gold nucleus. Sketch lines to show the electric field between these two lines of equipotential. Okay, that's kind of simple. You just draw outwards lines, I guess. So you start from there. So these are the electric field lines, okay? How do we know that they grow outwards? Because the nucleus always has positive charge, okay? So that's a positive charge in there. So remember that to find the equipotential lines, you assume that there is a positive test charge Q plus Q, a very small positive test charge, and that test charge will be pushed away from the positive charge of the nucleus. Okay, so that's the answer. Okay, part 2. The 40 volts line is drawn to scale correctly. Deduce whether the 10 volts equipotential line is in the correct scale position. Okay, so remember that V is KQ over R. Okay, so let's say that, so if we solve for R is KQ over V, right? So let's divide R1 over R2 will be equal to KQ over V1, okay? And for the second radius, we will have KQ over V2, okay? So KQ cancels. So this is equal to, V2 over V1. Therefore, R2, the one at the 10 volts, is equal to, let me think, V1 over V2 times R1. So it should be at about 4 times R1, okay? Okay, so let's go back here. One of the tools you can use is a ruler, I think. Can we find it? Let's see. Ruler. Okay, good. Okay, so you see that this is about 1 centimeter, whereas this is at 2, 3, 4 centimeters. So it works. That's correct. Okay. Does this make sense? So you see that from here to here we have one. Oops. Let's erase this. Okay. So I don't know why I cannot draw. So that's 1 centimeter and this is 4 centimeters. Okay. So that's that actually works. Okay, let's go back. How do we get rid of the ruler now? Okay. All right. So yes, it works. I mean, up to scale. Okay, question 3. An alpha particle moves from the plus 10 volts potential to the plus 40 volts potential. Calculate the increase in the potential energy of the alpha particle in electron volts. Okay, so the electric potential energy EP is equal to Q times delta V. So since we are dealing with an alpha particle has a charge of plus 2e, right? And the change in potential difference is 30 volts. So that's immediately 60 electron volts, okay? Just like that. Okay, question 16. Hockey is a sport played with a stick and a ball. The player tries to hit the ball with part of the stick called the heel as shown. The player swings her stick so that the heel moves horizontally in a circle of radius 0.8 meters across the ground as shown below. So the motion is probably something like that, or in the other direction. Okay, so let me erase this. It takes a time of 0.22 seconds for the heel to move through an angle of 1.3 radians. Calculate the speed of the heel. Okay, so the speed is related to the angular velocity via omega times r, right? And omega is simply the change in angle over the change in time times r. So let's plug in numbers. Delta theta is 1.3 radians, and radians have no units, so you use them as is, over 0.22 times 0.8 meters. If we do this calculation, which for some strange reason, I'm sorry, I don't have in my notes, and I have to perform live, we get 4.72 meters per second. Okay, and if we go to the mark scheme, which I opened, okay, it's over here. Okay, 4.72 meters. Okay, let's move back. All right. Part B. A ball has a speed of 13 meters per second. The heel has a momentum p heel of 3 newtons times seconds in the direction of the dashed line as shown. The heel collides with the ball and stops. Okay. The speed of the ball after being hit by the heel is 16 meters per second. Deduce whether momentum is conserved for this collision by completing the vector diagram below. A scaled line representing p heel is shown. And we're given the mass of the ball, which allows us to calculate. Okay, here we will not analyze. Okay, normally you analyze momentum into components, so something like that, but this is not how it will work now because we are asked to use the diagram. Okay, so to use that, we need to find the magnitude of the momentum before, so B ball before. And I'm not using arrows because we are talking about the magnitude. So that's m times v, so 0.16 kilograms times 13, which gives, let me do it, times 13, 2.08 newtons seconds, okay? And p ball after is 0.16 times 16, which yields 2.56 newtons seconds. Okay, so now since this is scaled, let's actually measure it. Let's bring the ruler and let's measure this vector. So okay, we need it to be at 90 degrees. Okay, so that's 6 centimeters. Okay, so you can see it. Okay, so p heel is 3 newton seconds, and it's proportional to 6 centimeters. Actually, let me use the proportionality symbol. Okay, something like that. Okay, therefore, we have to multiply by 2 to find the proportionality for the momentum before and after. So, okay, if we multiply by 2, we find 4.16 centimeters should be the length of the momentum vector before, and 2.56 times 2 is 5.12 centimeters, has to be the length of the momentum vector of the ball after, okay? And also recall that it has to make a 56-degree angle with, so I'm trying to say that this is the momentum of the ball before, and this angle should be 56 degrees, okay? Let's bring up the ruler again, see if we can actually do that. Okay, so we need the, you can actually set angle. Okay, so let's set it to 56. Okay, 56. Okay, confirm. Good. Okay, and we also need it to be there. Okay, and we need to draw 4 centimeters, so that's okay. Okay, that's about 4.1 centimeters. Okay, that makes sense. Okay, let's say that this vector is P, B, B4, okay, and this angle should be 56 degrees. Okay, now if you bring back the ruler, this distance over here, let me use a red color. This is the momentum after, so the length of this vector should be 5.12 if everything works, if momentum is conserved, and so on. Okay, so let's bring up the ruler and see if that's true. Okay, here's the ruler. So let's line up the 0. Okay. Let me think. That doesn't seem to work, to be honest. And let's see, why is that? Is that the 56 degrees, or maybe that's, okay, that's 90 minus 56. So that's actually a 34-degree angle, the way the ruler works. So we have to delete this. Okay, let's press the ruler again. Okay, let's actually bring it back here. So what I'm trying to say is that it actually measures with respect to the horizontal. Okay, so we actually have to set it to set angle. Let's set it to 34, which is the complementary to 56. Okay. Okay, so okay, and we need again 4.1 centimeters. So we need that. Okay, let's get the ruler away. Okay, now that's 56. Before it was 34 because it measures with respect to this angle. So anyway, okay, now if we bring back the ruler, I hope I haven't confused you or lost you so far. If we bring back the ruler and measure this, I bet you it's 5.1. And yes, it is. Okay, you see how it works? So now this angle, let's use a red color. Sorry, this vector. Let's actually get the ruler away. Okay, so this is now P of the ball after, and this is P of the ball before. Okay, I hope this makes sense. And let's move on. Okay, this was a little bit more involved than I wanted it to be, but okay. So the next is to deduce whether the collision is elastic. For a collision to be elastic, we need the kinetic energy before to be equal to the kinetic energy after, right? So to calculate the kinetic energy, we need the mass of the ball and the initial and final velocity of the ball, which you have, but we don't have the mass of the heel. But you can calculate it because they give us the speed of the heel before the collision as 5 meters per second. And remember that they also give us the momentum of the heel. Okay, so P of the heel is equal to the mass of the heel times the velocity of the heel, right? So the mass of the heel is just 3, which is the momentum of the heel before, over the velocity, over 5, which is 0.6 kilograms. Okay, so the kinetic energy before is 1/2. Actually, let's use P heel squared over 2 mass of the heel plus P ball before squared over 2 times the mass of the ball. Okay, so the P heel before is 3 squared over 1.2, which is 2 times 0.6, plus the momentum of the ball before. We calculated it, that's it, 2.08 squared over 2 times the mass of the ball, which is 0.16, so 0.32. Okay, and this gives us, let me think, 9 over 1.2 plus 2.08 squared over 0.32, so 21.02 joules. Now the kinetic energy after is just the P of the ball squared after over 2 times the mass of the ball, which is 2.56 squared over 0.32. This is not gonna work. So let's see, 2.56 squared over 0.32 gives, actually it's close, 20.48 joules. Okay, so pretty much 0.5 joules are lost. So the collision is not strictly elastic. Okay, so some energy is lost actually. So some energy is lost, so not elastic. But let's check the mark scheme. So let's see. Okay. So not elastic collision. Okay, so this is what they say as well. So we are good. Let's go back. And let's move to question 17. An aeroplane flies in a horizontal circular path whilst waiting to land at an airport. The airplane flies at a constant speed v around a horizontal circular path of radius r. The diagram shows 2 positions A and B of the aeroplane on its circular path. The acceleration of the aeroplane is A. Derive the expression A equals v squared over r. You should include a vector diagram. So, let me think. So let's actually use a clean page. So if we have a circle, actually we can draw a circle using this thing. Okay. Oops. Okay, that's the circle. We can actually make it larger. All right. Okay. And we can also, yeah, let's keep it there. Okay, that's good enough. So that's the center, say. Okay, and that's point A and point B. That angle is theta, and the vectors are tangent to the circle, the velocity vectors, that is. Okay. So when the plane moves from A to B through the angle theta, and this is r, by the way, and let's call this C, we have the triangle CAB, right? So let's draw a triangle CAB. Okay. C A B. Okay. Let's call this delta theta. Let's call this delta S, which is the displacement, and this is r by definition. Okay. And let's assume that this angle theta, which becomes delta theta there, is really, really small, okay? Very tiny, like 0.1 radians or something like that, okay? Since the velocity vectors are tangent to the circle, okay, they are perpendicular to this radii, right? So actually the vector, this vector of the velocity v at A and this vector of the velocity v at B also make an angle delta theta, okay? Can you see that? Because they are mutually perpendicular to the radii pretty much, okay? So we can also draw another triangle where the sides are now the velocities, okay? And this is delta theta, the angle between the velocity at A and the velocity at B, which is exactly the same as this angle theta, okay? And this is just delta V, the change in velocity, okay? So for small, I will need another clean page, I'm sorry. So for small delta theta, okay, since these triangles are similar because they have two sides are equal and the angle between these two sides is delta theta, which is the same. This means that their sides are proportional. So delta S over delta V is equal to R over V. So delta V is V over R times delta S, okay? And if we divide by time, delta V over delta T is V over R times delta S over delta T, which means that A, because A is the change in velocity with respect to time, is V squared over R, because recall that this is just V, right? And also here we assumed that delta S is a straight line, which is true if delta theta is really small, close to zero. Okay, so that's proved. That's it. Okay, I hope this makes sense. It's a little bit difficult to understand it, so please work on this on your own. It's going to help you understand, okay, if it's not already clear. Right, part B. The aeroplane flies in a horizontal circle by tilting to one side in a movement called banking. The aeroplane creates an upwards lift force which acts in a direction perpendicular to its wings. The diagram shows this lift force when the aeroplane is banking, okay? Explain how banking allows the aeroplane to fly in a horizontal circular path. So, okay, let me think about how I want to discuss this. Okay, so first of all, this circular path is will look like something like this, okay? So I'm trying to say, imagine this, actually this is a bad circle that I drew. So imagine a circle, something like when we draw the magnetic field line, magnetic field lines. So imagine a magnetic field coming out of the page. On here, the plane comes out of the page, and here it goes into the page, something like this. And then there is a circle connecting this motion, okay? So to do that, I'm pretty much trying to say that there must be a resultant force to the left of the plane, which will allow it to undergo a circular motion with the plane coming out of the page and towards us, and then going in a circle around the page and then into the page and something like that. I hope this makes sense. It's difficult to explain outside of the classroom, okay? So what I'm trying to say is that we can analyze the lift into a vertical component. Let's call this angle theta. So this is L cosine theta, and this is L sine theta, okay? So it's this component of the lift that makes the aeroplane bank, okay? So, so from the forces here, the weight must be equal to L cosine theta, because there is no up or down motion, okay? And then L sine theta should be mv squared over r, where r is the radius of this banking. Okay, so we can write down that the vertical component of the lift counteracts the weight, but the horizontal component of the lift acts as a centripetal force for circular motion as it is perpendicular to the velocity. To v, okay, and v, okay, what I was saying is what I called the plane earlier is actually the velocity. So the velocity of the plane comes out of the page here, okay, so this is the velocity, it comes out of the page on this side, and then the velocity goes into the page, okay, and therefore the lift is actually perpendicular to the velocity in this case, and this explains it, okay, so this is why planes bang, okay. So to understand it, get your pencil and make it perpendicular to the page as you write, okay? And that's the aeroplane, okay, that comes out of the page and then into the page. Okay, part 2. During banking, let me see, the angle between the wings and the horizontal is 5.2 degrees. Calculate the radius of the circular path when the aeroplane flies at a constant speed of 530 meters per second. The mass of the aeroplane is 4.1 times 10 to the 5 kilograms. Okay, so we're going to use these two equations that we wrote down earlier. Okay, so L cosine theta is equal to m times g. So the lift is equal to m times g over cosine theta. Okay, but we can plug this into the other equation, which is L sine theta equal to m v squared over r. So r is mv squared over L sine theta, but we can plug L in, so we get that r is mv squared over m times g, and then we have sine theta over cosine theta, m cancels, so we get v squared over g, and then tangent of theta, because sine of theta over cosine of theta is tangent of theta. Okay, so r, if we plug everything in, ends up being 314.6 kilometers. Okay, that's a large radius. And that's the answer. Okay. Question 18. Mass spectrometry is used to determine the masses of different isotopes of an element. Atoms of the isotopes are ionized and accelerated. They pass through a velocity selector, this part over here. They pass through a velocity selector and into a region with a uniform magnetic field as shown. And again, I happen to have a PhD in nuclear physics, and at the University of Notre Dame, where I got my PhD from, and Michigan State University, where with which Notre Dame collaborates, they both have this kind of things. For those of you who are interested in nuclear science, okay. Now, question A. An ion accelerator uses an electron beam to ionize atoms of oxygen gas. The positive ions are then accelerated across a high potential difference between an anode and a cathode, as shown in the diagram below. The cathode has a hole in it so that the accelerated ions may pass in a fine beam to the velocity detector. Okay, the electric field strength between the anode and the cathode is 7.5 times 10 to the 5 volts per meter. Calculate the potential difference between the anode and the cathode. Okay, this is simple. E is V over D for parallel plates only, remember that. So V is E times D, so 0.06 meters times 7.5 times 10 to the 5 yields 45,000 volts or 45 kilovolts. That's quite high. Right. Question 2. A stationary oxygen ion is formed halfway between the anode and the cathode with a charge of 1.6 times 10 to the negative 19 coulombs, which is the charge of one electron pretty much. One proton, sorry. Show that the velocity of the ion as it passes through the hole in the cathode is about 5 times 10 to the 5 meters per second. The mass of oxygen ion is 2.7 times 10 to the minus 2 nt6. Okay, we need to calculate the velocity and we can use Suvat equations. This is one of the things about the A-level. You should remember, guys, Unit 1 and Unit 2, even though it rarely comes up. Sometimes they have questions like this where you kind of need information from the past units. So let's go and see. So in case you don't remember, you can just go to the back of the paper. Let me see, over here. So we will need this equation pretty much. Okay, the final velocity is equal to the initial velocity plus 2 times the acceleration times the length. Okay, so let's see how this will work. I think we will need a clean page maybe, but anyway, okay, so v squared is u squared plus 2as. We know that it's halfway through the magnetic, through the field, so s is simply 0.03 meters. The initial velocity is 0, so we need to find the acceleration. How do we find the acceleration? The force exerted on the ion is equal to mass times acceleration, and what is that force is q times e. Okay, so A is simply q times e over m, where q is 1.6 times 10 to the negative 19, e is what was given to us here, and m is the mass of the oxygen ion. Okay, so oops, so u squared, so that's 0. So this is the mass of the ion which goes there. Okay, and if we plug everything in, we find 4.4 times 10 to the 12 meters per second squared. Okay, s is 0.03, so v squared is 2 times 4.4 times 10 to the 12 times 0.03, and if we plug everything in, we find v equal to 500,000, 16,395.2 meters per second, very close to what we are asked. Okay. Part B. Oxygen ions enter the velocity selector with a range of velocities. The velocity selector allows ions with a specific velocity to travel in a straight line as shown. Plate P is positive and plate Q is negative. Okay. A uniform electric field between the plates acts on an oxygen ion. A uniform magnetic field acts so that the magnetic force on the oxygen ion is in the opposite direction to the electric force. Explain the direction of the magnetic field. Okay, so the oxygen ion is positively charged. So since it's positively charged, the electric force is gonna be Q times the electric field. It's gonna point downwards. So the magnetic field needs to be upwards. Okay, so this is the magnetic force. I'm sorry. So Q. Oops. What am I doing? Actually, let's write just Q. Oops. Q V B. Okay, the velocity is in this direction. Okay, and for the remember Fleming's left hand rule. So my index should point in the direction of the magnetic field. My middle finger should point in the direction of the velocity, and then my thumb should point in the direction of the force. So my middle finger points to the right, just like the velocity does. If I put my finger into the page, then my thumb points upwards as we want. Okay, so B must be into the page. Okay, so B must be into the page so that QVB is upwards, so that it balances Q times E. Okay, and you can write here Fleming's left hand rule. Okay, I don't know why I'm writing in red, but I hope it makes sense. Okay, part 2. The velocity selector is used to produce a beam of oxygen ions traveling in a straight line with a speed of 5 times 10 to the 5 meters per second. Calculate the magnetic flux density of the magnetic field that is required. And they give you the electric field strength between the plates. Okay, so Q times E must be equal to Q V and B. So Q cancels. So B is just E over the velocity. Okay, so 10,500 over 5.5 times 10 to the 5, which is the velocity, gives 0.021 Teslas. Okay, and last question in the test. After passing through the velocity selector, a beam of oxygen ions with the same velocity enters a region of uniform magnetic flux density. Different isotopes of oxygen can be present in the beam. Explain why the detector will only detect one particular isotope. Okay, recall that QVB, the force on that ion, or all of the ions pretty much, is mv squared over r. Okay, so this v cancels. So r is equal to m times v over qb. Okay, so isotopes with different mass, even though the velocity is the same, okay, and q is the same, b is the same, but mass is not the same. So isotopes with different mass will have a different radius. Okay, so they won't go through, pretty much. And this summarizes the test. Thank you guys for those of you who are following until the end. I don't know how many of you are following until the end. Please write in the comments if you actually watch through the end. And I don't know, just say hi. Maybe write where you are watching from. And I hope these videos are useful. See you in the next one.